Right now, a torrential rush of fluid is cycling through your vascular system, pushing roughly 5 liters of blood through microscopic tunnels every single minute. And hiding inside that massive volume of fluid is a constant, silent accumulation of metabolic waste. In a hospital setting, this hidden accumulation can trigger an immediate, multi-system alarm. A patient presenting in the emergency room with fulminant acute kidney injury is standing on the precipice of a fatal cardiorespiratory collapse, driven by a hyperkalemic cardiac arrest. Yet the specific molecule that trips the laboratory's critical panic threshold, a chemical called creatinine, poses absolutely no direct threat to the patient. Even at massive, off-the-chart concentrations, it does not damage organs or tissue. It is inherently non-toxic. Most of human biology focuses on complex active machinery, proteins that build structures, or nucleic acids that encode genetic instructions. Creatinine is the exact opposite. It is an entirely passive, inert waste product. Because it cannot harm the body, its sudden buildup serves a different purpose. It operates as the ultimate biological tracking device, a pure, indirect proxy warning us of an unseen and highly lethal metabolic ruin. To understand why we rely on this specific molecule, we have to look at the mechanics of high-velocity physical locomotion. When early terrestrial animals sprinted from predators or hunted down prey, they burned immense amounts of energy, generating heavy loads of nitrogen waste. They required a disposal channel that could clear this toxic nitrogen quickly without overloading the liver. Nature's solution to this metabolic bottleneck is incredibly ancient. We see this exact biochemical infrastructure conserved across the entire chordata phylum, tracing in an unbroken line all the way back to primitive hagfishes on the ocean floor. This system begins inside your skeletal muscle. To support intense physical exertion, muscle fibers rely on a high-volume anaerobic energy reserve called phosphocreatine. Think of it as a rapid discharge battery pack that powers immediate heavy lifting. Every 24 hours, a highly predictable, fixed fraction of this phosphocreatine pool, about 1.6 to 2%, spontaneously degrades without any enzyme activation. It cleaves off a high-energy phosphate group, bends back on itself, and snaps into a tightly locked ring. This locked ring is creatine. Weighing precisely 131.13 grams per mole, it operates as a small, neutral, coplanar molecule that is highly soluble in water. Once closed, this carbocyclic architecture completely resists any further cellular reutilization or breakdown. The human body simply cannot pry it back open. By producing a locked ring, the body can flush the nitrogen waste straight into the blood without creating a complex enzymatic bottleneck. It acts like molecular sawdust flying off a high-powered buzzsaw. Because it is generated at a steady state and lacks the receptors to bind to mammalian tissue, we can measure the pile of sawdust to calculate exactly how fast the body's internal filtration system is running. The moment creatinine is generated in the intracellular fluid of your skeletal muscles, it diffuses passively across the cell membrane and outward into the extracellular fluid of the blood plasma. Because it holds a neutral charge and does not bind to large serum proteins, it requires no protective carrier molecules. It circulates freely through the vascular system, heading directly for the kidneys. At the renal filtration boundaries, creatinine encounters glomerular slit diaphragms, microscopic, charged sieves. Being tiny and uncharged, it falls directly through, while larger proteins bounce off. Additionally, proximal tubule cells use active transport pumps to secrete remaining creatinine into the urine. Because muscle production is fixed and glomerular filtration is unimpeded, measuring the steady-state concentration of creatinine remaining in the blood provides a highly accurate, direct readout of your overall renal processing speed. However, interpreting that readout requires strict mathematical context. Relying on a raw serum creatinine number in a vacuum, without accounting for a patient's age, sex, and physical state, leads to critical diagnostic failures. This chart maps glomerular filtration against age and muscle mass. As humans age, losing muscle means producing less creatinine. Therefore, an elderly patient's seemingly healthy reading actually masks a severe loss of functional nephrons, concealing advanced chronic kidney disease. We see a similar yet inverted blind spot during pregnancy. In the first trimester, maternal blood volume expands significantly to support the fetus, driving the kidneys into a state of physiological hyperfiltration. They increase processing speed by 50%, flushing out creatinine far faster than normal. This accelerated clearance drops the healthy baseline down to between 0.4 and 0.7 milligrams per deciliter. Consequently, if a pregnant patient registers a value of 1.0, a number signifying excellent health in a non-pregnant adult, her renal filters have actually crashed. Clinical pathology avoids these lethal traps by applying standardized age and sex-adjusted equations, like the CKD EPI formula. These mathematical models translate the raw chemical concentration back into the true biological reality of the patient. When that biological reality involves an acute kidney injury, the mechanical architecture physically fails. The glomerular filtration barriers clog or collapse entirely, bringing the natural clearance of creatinine to an abrupt halt. As the unharmed creatinine rapidly backs up into the vascular pool, it signals a deeper crisis. If the filters are broken enough to trap this tiny ring, they are inevitably trapping lethal secondary metabolic waste alongside it, specifically hydrogen protons and potassium ions. Retained potassium is exceptionally dangerous. As it accumulates, it alters the electrical resting potential across the cellular membranes of the heart. This blocks critical ion channels, triggering severe hyperkalemic cardiac arrhythmias that manifest on an ECG as sharp, peaked T waves and widened sine wave QRS complexes. Facing imminent cardiac arrest, emergency medicine deploys a strict 3-tier response protocol. Step 1 is immediate membrane stabilization. Clinicians infuse intravenous calcium gluconate. This does not lower the potassium. Instead, it stabilizes the cardiomyocyte membrane potential, raising the threshold for fatal electrical short circuits and buying the patient vital minutes. Step 2 is intracellular shifting. By administering a heavy dose of regular insulin paired with intravenous dextrose, clinicians artificially hyperactivate the cellular sodium-potassium pumps. This aggressively drags the dangerous potassium out of the vascular space and shoves it deep into the cell cytoplasm. If the potassium resists shifting, or if the kidneys show no signs of recovery, the team advances to Step 3, extracorporeal elimination. Mechanical hemodialysis forcibly pulls the blood from the body, physically filtering out the creatinine, potassium, and acidic waste. When the natural internal architecture completely fails, medicine must manually replicate the homeostatic clearance mechanism from the outside to prevent multi-system death. But before any of these emergency protocols are deployed, the critical data must first be verified by the clinical chemistry analyzer. The absolute accuracy of this laboratory pipeline dictates the entire diagnostic response. For decades, the global standard for measuring these levels was the classic Jaffe colorimetric assay. This method introduces a chemical called alkaline picrate into the blood sample. When it binds to the 5-membered creatinine ring, it forms a measurable red-orange complex. However, this chemical reaction possesses a fatal structural flaw when testing patients with uncontrolled diabetes. Patients in diabetic ketoacidosis produce massive volumes of acetoacetate, a keto acid bearing a striking structural resemblance to the creatinine ring. The alkaline picrate reagent cannot tell the difference. It binds aggressively to the acetoacetate, generating the exact same orange signal, yielding a falsely elevated reading. This chemical illusion, termed pseudo-hypercreatinemia, tricks the system into sounding a kidney failure alarm when the renal filters are actually perfectly fine. Modern laboratories solve this by upgrading to enzymatic spectrophotometry. Instead of a simple color dye, this method utilizes a highly specific multi-enzyme cascade. The primary enzyme, creatininase, acts as a precision lock that only fits the exact geometry of true creatinine, completely ignoring the keto acids. Understanding the structural geometry of these laboratory assays ensures that pathologists catch these chemical illusions. It prevents the medical team from subjecting metabolically stable diabetic patients to aggressive, unnecessary treatments like mechanical dialysis. The laboratory must also navigate pre-analytical traps, errors introduced before the blood ever reaches the machine. The most common is the postprandial cooked meat surge. Animal meat is essentially skeletal muscle packed with free creatine. Cooking that muscle on a hot grill forces a chemical conversion, turning raw free creatine directly into exogenous creatinine. Consuming a large steak delivers a massive dose of pre-made waste directly into the gut. This triggers a transient postprandial spike, temporarily inflating serum creatinine levels by up to 30% and artificially simulating an acute kidney injury. To achieve an accurate, steady-state reading of true renal function, clinical protocols dictate that patients must complete a strict 12-hour overnight fast prior to their blood draw. Once a clean sample is secured, the internal quality control demands are relentless. To ensure mathematical models yield accurate filtration estimates, clinical chemistry lines target a strict total allowable error of just plus or minus 0.1 milligrams per deciliter. This precision guides diagnostic stewardship. Under the Choosing Wisely guidelines, clinicians are advised against ordering repeated panels on stable patients sooner than 24 hours apart. Because it is a steady-state marker, it requires physical time to accumulate or clear through the nephrons. Testing any earlier simply wastes resources. Looking ahead, the horizon of waste clearance extends into the microbiome. Specific anaerobic gut bacteria naturally express creatinase enzymes, using our waste as their fuel. During advanced kidney failure, these microbial populations expand, acting as a minor extrarenal clearing loop, a biological failsafe operating quietly in the intestinal tract. Ultimately, this tiny neutral ring of molecular sawdust connects the heavy kinetic output of our skeletal muscles to the delicate filtration sieves of our kidneys. By tracking its continuous passive flow, human medicine maintains a direct line of sight into the high-stakes fluid dynamics that keep the electrical grid of the heart beating.